All right, welcome to your last section in Chapter 3. In this last section, we are going to be discussing simulations and how simulations can help us make predictions. Remember the experiments that we talked about in the last section. Sometimes doing experiments is not always practical, so we are going to discuss how simulations can help us to make predictions. Okay, so after this section, what you're going to be able to do is interpret probability as a long-run relative frequency, and we'll talk about what that means in a minute. And the main part of this section is using a simulation to model chance behavior. Okay, so using the simulation to model chance behavior, just make sure as you're going through this section that you're paying careful attention to how the simulation is described. And in this section, it's going to be very important to understand that when you're using a simulation to model our chance behavior, you should be able to take your All right, so let's just take a quick minute and talk about the idea of probability. So chance behavior is unpredictable in the short run, but has regular and predictable patterns in the long run. So for example, if we're talking about tossing a coin, if you toss a coin 3 times, you could get all 3 heads, you could get all 3 tails. But if you toss a coin 3,000 times, which is the long run, most likely what's going to happen is those probabilities of 50% of getting heads and 50% of tails are going to even out, and in the long run you should get about 50% heads and about 50% tails. Same thing with rolling a die. If you roll a die 3 times, all 3 times you may get 6s. You may get lucky when playing Monopoly. However, if I were to roll that die 6,000 times, that would be the long run. I should hopefully in the long run be able to get 1,000 ones, 1,000 twos, 1,000 threes, 1,000 fours, 1,000 fives, and 1,000 sixes, because each of those 6 numbers have an equal chance of being rolled when I roll the dice. So what we just talked about was the law of large numbers. Hopefully you've heard of this in some of your other math classes. So the law of large numbers says that if we observe more and more repetitions of any chance process, it doesn't matter what it is, the proportion of times that a specific outcome occurs approaches a single value. So for example, what is the probability when I roll a dice of getting a 1? Well, it's 1 out of 6 because there's only one 1 out of all 6 of them. So if we roll the dice 6,000 times, most likely that probability of going to get a 1 is going to approach 1 out of 6. More likely than it happens in the short term. So basically, what does this tell us? It tells us that the more trials we have, the closer the theoretical probability matches the empirical probability. Well, what does that mean? Theoretical probability is what should happen. When I roll a dice 6 times, each has a probability of 1/6 of occurring. The empirical probability is what happens when you actually do the experiment. So if you roll your dice 3 times, what's the probability of getting a 1? Well, every time it's 1/6, but if I get a 6 every time, my probability of those 3 rolls, or the empirical probability, was 0 because I didn't get a 1. Okay, so the theoretical probability tells us what happens over the long run. All right, so let's talk about tossing a coin. All right, the probability of getting heads is 1/2 and the probability of getting tails is 1/2. All right, so this is just looking at your proportion of heads. So since it is 50%, all right, so when I toss it 1 time, it was 100% because I got heads, okay? When I tossed it the second time, I had 1 heads and 1 tails, so that proportion was 50%. Okay, notice how it's going up and down, all right, as I'm tossing it, because this is saying that this is talking about the number proportion of heads. It decreases when I get tails, all right, so at let's say about 20 tosses, it's getting close to 50%. But what happens when I do this 500 times? All right, so notice my proportion of getting heads is below 50%, above, below, but notice how my graph sort of evens out at the end, and at the end of 500 tosses, my theoretical probability is about 50%, and I got about 50% of heads when I tossed it 500 times. So that's your law of large numbers. All right, so what exactly does probability mean? All right, number one, the probability of any outcome of a chance process is between 0 and 1. So what's the probability that it's going to rain? It's either yes or no. So the probability that it doesn't rain is 0, and the probability that it does rain is 1. Okay, that describes the proportion of times that the outcome would occur in a very long series of repetitions. So that's talking about our toss of the coin. What's the probability of getting a 6? It's 1 out of 6. If I were to toss that coin 500 times, hopefully, or roll the dice 500 times, hopefully the probability of getting a 6, which is 1 out of 6, would get closer and closer the more repetitions that I do. All right, so what exactly does it mean to interpret probability? So if you get a question that says interpret the probability, it is in the long run, what's the relative frequency? So if I toss a coin 500 times, in the long run, what's the probability or what's the relative frequency that I should get tails? 50%. After many, many, many rolls of the die, what's the probability that we'll roll a 6? Should be 1 out of 6. What do you predict will happen? So interpreting the probability is saying after many, many, many rolls of the dice, tosses of the coin, what do you expect the probability to be? All right, so here's an example. So what's the probability of rolling 2 die and getting a sum of 7? Let's interpret this value. Well, here's just a quick table of rolling 2 die. Okay, and then here's the sums. 1 plus 1 is 2, 1 plus 2 is 3, so on and so forth. I have the 7s are highlighted. Okay, so what is the probability of getting a 7? If we notice, there's 36 rolls of the die. 1, 2, 3, 4, 5, 6. So there's 6 ways that I can get a 7. So if I were to roll these 2 die 5,000 times, what's the probability of getting a sum of 7? Well, it's going to be 6 out of 36 or 1 out of 6. So how would I write that? So in statistics, it is often really important to make sure you understand what interpret means. So if the 2 die were rolled many, many, many times, you could expect a sum of 7, 6 out of 36 or 1/6 of the time. Okay, so interpret is many, many, many times, and then stating what the probability is in context, always in context. All right, so the idea of probability seems pretty straightforward. However, there are a couple myths about chance behavior that we must address. So just be careful with this. The myth of short-run regularity. So the idea of probability is that randomness is predictable in the long run. It is not predictable in the short run. So our intuition tells us that random phenomena should be predictable in the short run, but it's not. Okay, the law of large numbers does not apply to the law of short numbers. There's no law of short numbers. It's just the law of long numbers, which is the same as the long run. All right, so the probability does not allow us to make short-run predictions. So let's just say we're rolling a dice 10 times, you're playing Monopoly, and get a 3 50% of the time. So even though you've gotten a 3 50% of the time, you are not more likely to get a 3 on the 11th roll. You still only have a 1/6 chance of getting a 3 on the 11th roll. The probability of getting a 3 every single solitary time is changing. So the long run predictions haven't played out yet because there aren't enough trials. This is just the short run. Okay, so the long run predictions tells us that the probability sort of evens out. You're giving every number on that die an equal chance of being rolled by rolling it 1,000 times or 500. Okay, the biggest mistake is to apply the law of large numbers to a too small number of trials. All right, so there's no specific rule, just logically think about it. 5 trials is not very large, 500 is a lot. All right, so let's just quickly talk about the myth of the law of averages. All right, so probability tells us that random behavior evens out in the long run. Future outcomes are not affected by past behavior. So when I roll a die, the probability of getting a 6 evens out after 5,000 rolls. Okay, the probability of getting a 6 is 1 out of 6. The future outcomes are not affected by the past behavior. So when I roll a 6 a second time, that second roll is not affected by what I got on the first one. That is, past outcomes do not influence the likelihood of an individual outcome occurring in the future. Same thing with tossing a coin. If I toss a coin and get tails, okay, that's not going to affect when I toss the coin in the future what I get. Just because I got one tails doesn't mean I'm going to get second tails the second time. This also means that streaks, you talk about streaks, especially in sports and in poker games, card games, Vegas, don't influence future outcomes. If you roll a die and get a 6 5 times in a row, this does not mean that you're more likely to get a 6 in the future. Basically, you got lucky. Okay, so streaks are part of the random probability process. You just got lucky if you got one of the streaks. Okay, so just take a quick look about the article about Joe Dimaggio's hitting streak. It's actually pretty interesting. So in this article, the author claims that one of the most remarkable streaks in baseball history is Joe Dimaggio's 56 consecutive game hitting streak. But in fact, this is actually not very remarkable at all. Obviously, it's extremely unlikely for any particular player to have a hitting streak that long. But when we look at all of the players in all of the seasons in all of baseball history, we will expect some very unusual performances. So to investigate this, to see, hey, was his 56 consecutive game hitting streak, was it likely or unlikely? This is what we're going to talk about in this section. They simulated performances of every baseball player in every season for a total of 10,000 times. So in each of those 10,000 simulated histories of baseball, they recorded the longest hitting streak. All right, so they did this 10,000 times and looked at the hitting streak. So in about 42% of the trials, someone had a hitting streak of at least 56 games in a row, with the longest being 109 games in a row. So his hitting streak wasn't that unusual. It's just part of the chance process. Okay, so the imitation of chance behavior based on a model that accurately reflects a situation is called a simulation. So basically, we're not actually going out and having the baseball players hit 10,000 times. Okay, we're conducting a computer simulation in order to say, okay, is this likely or is this not likely? I'm not actually going to roll the dice 5,000 times. I'm going to use a computer-generated software in order to simulate rolling a dice 5,000 times. So why do we perform simulations? We perform simulations to estimate the probabilities when the theoretical probabilities are too difficult to estimate. So I'm not actually going to sit here and roll a dice 5,000 times. All right, so how can I get the probability of rolling a 6 without actually doing it 6,000 times or 5,000 times? So it's easy to estimate probability with die, cards, and coins. That's not too bad. However, it's a little bit more difficult when we start talking about sort of real-world situations instead of dice and cards and coins. So what is the probability that an AP Stat student in Fairfax County is taller than 6 feet? Well, maybe I don't want to go measure every single AP Stat student. Can I use a simulation to figure out what the probability is? What's the probability that when you go to McDonald's, you're going to get the toy you want? Also, McDonald's had that Monopoly game. What's the probability that you have to go to McDonald's only 10 times to get all the Monopoly pieces that you needed? I don't want to go to McDonald's 800 times to figure out that probability. I can use a simulation to figure out how many times I need to go to McDonald's to get the Monopoly piece that I want. Okay, so a simulation is going to make it a lot easier to do. It's sort of just like a mock trial of what will happen over. So how exactly do we perform a simulation? The first thing you're going to do, just take a minute and go ahead and write these down, and we will be going through each of these 4 processes in 3 examples. So in order to perform a simulation, number 1, we're going to state the assumptions about chance behavior. So what does that mean? So what is the probability that I'm going to have to go to McDonald's 10 times to get all 10 pieces for the Monopoly game? Okay, so that's identifying the probabilities related to the situation. Then make sure we understand that the trials are independent of each other. So for example, when I roll a dice, if I roll a dice and get a 6, when I roll a dice a second time, is that second roll based on the first roll. Absolutely not. When I go to McDonald's and I get a game piece, when I go a second time, does what I got the first time affect what I got the second time? Absolutely not. All right, then our plan, so we're going to have this 4 methods: state, plan, do, conclude. Sort of get used to that. That's what we're going to be using all year: state, plan, do, conclude. It's easy to remember. So our state, what are the assumptions about chance behavior? Plan, we're going to describe how we're going to use a chance device to imitate one repetition. Now that device can either be a graphing calculator, a computer software, or a table of values of random integers. We're going to tell what we're going to record at the end of each repetition, and we're going to assign digits to represent our outcomes. So for the example, 1 would represent the number 1 on a die. Number 2 would represent the number 2 on a die, and I'll explain what that means in a minute. Okay, so if you are using a random integer table, you have to be specific about how we're going to perform the simulation. So for example, if you have a template, we're going to state, starting at line 2, on the random integer table, we're going to read every how many digits, so 2 digits. That's going to be coming from how you assign the digits. Select the numbers that fall between 1 and 5. Omit 0, 0 and repeated numbers. So remember, just like in the previous section, whenever we were sampling, you have to state, are you omitting repeated numbers? And then we're going to record whether it's success or failure. So success basically is getting the chance behavior that we want. Failure is not getting the chance behavior that we want. We're going to identify the stopping point. So for example, after you've picked 4 hotels. So remember our hotel example, we had to pick 4 hotels or 4 stores in order to see how much money consumers were spending. We're going to say, okay, after we picked 4 hotels, we're going to stop. Okay, so do is performing the repetitions of the simulation. So the state, the plan told us how the simulation was going to occur. The do is actually doing the simulation. And then the conclusion is you have to use the results of your simulation to answer our question. So basically what you're doing is you're carrying out the simulation and you're interpreting your results. It will make much more sense once we go over an example. Notice how we have this 4-step process over here. All right, so that's going to be our state, plan, do, conclude. All right, also make sure that you state what the probability ended up being from your simulation in context of the problem. So what was the probability that you had to go to McDonald's more than 10 times to get all 10 game pieces? Okay, then state whether or not the probability you started with was reasonable. What are we going to use for a simulation? We had already said physical devices, so that could be like a calculator, a computer, a random integer table, and technology to perform our simulations. Okay, what should I watch out for when I'm performing simulations? Number 1, make sure during the plan section that you clearly communicate the method you're going to use to perform the simulation. You should be able to hand your piece of paper to somebody else. They should read it, and they should be able to say, okay, I know how to carry out the simulation. If you hand me a graphing calculator or a random integer table, I'm ready to go. Remember that when you assign labels, they have to be the same length. So this is the same thing in the last section. Don't assign 1 to 100. Those are 1 digit, then you'd have 2 digits once you got to 10, and 3 digits at 100. So you have to make sure you write 001 to 100. Those each have 3 digits. So all 3 digits are the exact same length. Okay? So if you are sampling without replacement, make sure to clearly state that you're going to ignore or skip repeats. So without replacement, even with replacement, when you're putting them back in, that's with replacement. Without replacement is not putting your numbers back in. But remember, when you use a graphing calculator or a random integer table, you can often get repeats. Make sure that when you're describing your simulation, you should be able to hand your description over to someone else, and they should be able to get the exact same results that you did following your instructions. All right, so let's just take a look at a quick example. So in an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring Jeff Gordon, Dale Earnhardt, Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. Don't you remember when you were a kid getting your box of cereal and seeing what kind of toy was in the inside? I remember that was exciting. So the company says that each of the 5 cars is equally likely to appear in any box of cereal. So basically you have a 1/5 chance of getting Jeff Gordon, 1/5 of getting Dale Earnhardt Jr., 1/5 Tony Stewart, 1/5 Danica Patrick, 1/5 Jimmy Johnson. So a NASCAR driver fan keeps on buying boxes of cereal until she gets all 5 drivers' cards. She's surprised when it takes her 23 boxes of cereal to get a full set of cards. Should she be surprised? All right, so what we do is we run a simulation to figure out how many boxes of cereal it's going to take her to get all 5 drivers' cards. Now, I don't want to go to the store and buy 800 boxes of cereal and then go through the boxes of cereal and see how many I needed to go through until I got all 5 drivers' cars. A, that's going to be really expensive. B, that's a lot of cereal I got to eat. And D, that's time consuming. So this is where we're going to use our technology to answer our question. So the problem is, what's the probability? So here's your probability statement that will take 23 or more boxes to get a full set of 5 NASCAR collectible cards. All right, so how can we use our state plan do conclude to answer? Sorry about this. If you take a look at the previous slide, over here, there was only 22. It only took us 20. There was no more than 22 repetitions to get all 5 different. Okay, so they should be surprised at how many boxes that you had to open in order to get all 5. It shouldn't take you 23. You got very unlucky. Okay, so I want you guys to take a minute and sort of try this one. Number 1, remember your state is always going to be what are you assuming about chance behavior, okay, and what probability are you trying to find. All right, number 1, we are assigning numbers to juniors and seniors to find the probability of drawing 8 or more names in order to get 4 seniors and 2 juniors. Okay, what's our plan? How can we do this? Well, remember we had 60 seniors and 30 juniors. So we're going to assign the numbers 01 to 60 to seniors and 61 to 90 to juniors. Now we're stating that we're omitting 91 through 00 because that's basically like 91 to 100. We're also ignoring repeated numbers since we're doing this without replacement. And the reason that we're ignoring repeated numbers is that I don't want to pick the same junior or the same senior twice. So I have assigned numbers, okay, to the chance process that I'm doing. So that's your plan portion. So your plan portion is always how are you going to assign numbers. Okay, so we're going to use our random integer table. We're going to start at line 101. You just have to look at your random integer table and pick a line to start at. It doesn't matter. Read every 2 digits. The reason it's 2 digits is because we assign 2 digits to the seniors and to the juniors until 4 seniors and 2 juniors are picked. So count the total number of names drawn and ignore repeats. Okay, so we're going to go for Okay, how did we do this? So here's just an example. So here were the numbers from my random integer table on line 101. So the first two was a 19, 22, 39, 50, 34, 05, 75, 62. So this was just me showing you, number one, what the numbers were, and then what it ended up being, juniors or seniors. Okay, so in this trial, we got lucky. It took us exactly 8 selections to get at least 4 seniors. So here's my senior 1, 2, 3, 4, and at least 2 juniors. So here are the results below 50 trials. So if you notice, actually, we got 1, 2, 3, 4, 5. We actually got 6 seniors before we got our 2 juniors. That's okay, because we wanted at least 4 seniors and at least 2 juniors. So here are the results of 50 trials. Okay, so the results of 50 trials are saying this line means it took 6 trials to get at least 4 seniors and at least 2 juniors. This here says it took at least 7 to get 4 seniors, 2 juniors, 8 to get 4 seniors, 2 juniors. So let's now answer our question. Okay, what is the probability that's going to take at least 8 selections? So that's why I have the stars highlighted on 8. That's going to take at least 8 selections to get at least 4 seniors and at least 2 juniors. So what's the conclusion? So in the simulation, 25 of the 50 trials, so we counted 8 or more, required 8 or more selections to get 4 seniors and 2 juniors. So the probability that it takes 8 or more selections is about 50%. So notice in this question, we weren't asking whether or not something was surprising. We were just estimating the probability that it was going to take 8 or more selections to get at least 4 seniors and 2 juniors. Okay, so let's just take a look at this next one. This next example is just asking the question, is something statistically significant and didn't happen by chance alone? So remember, statistically significant means that there was an outside force acting on it. Chance alone just means, okay, just by the random chance did this happen. Is Joe Dimaggio's hitting streak? That was pretty much just by chance alone. Okay. We don't know. Maybe it was something to do with his, fabulous baseball skills, but it could have been just by chance alone that happened. Okay, so go ahead and take a minute and read this. Press pause if you need to. Okay, so this specific question is asking us to carry out a simulation to answer the question, is it possible that the names weren't adequately mixed in a hat, or could this have happened by chance alone? So what exactly simulation am I carrying out? So the simulation that I'm carrying out is I'm taking all 18 students, okay, all 18 students, and I'm dividing them into 2 teams. So basically, I kind of want to know what's the probability, or what is the chance that all 9 of the teams, all 9 players on the team are going to end up being all math majors. Okay, so state look like? How's that going to look different than the other 2 questions that we looked at? So the state is, what's the probability that there will be one team with all math majors when randomly assigning 12 math majors and 6 stat majors to 2 teams of 9. So this is a little bit different. In the previous question, we were actually finding the probability. Okay, we were estimating what the probability would be. In the previous question, we were checking how many boxes we needed to get. In this question, we're saying, okay, is this statistically significant? Could this happen by chance alone? So what's the probability that there will be one team with all math majors? How can we do that? Okay, we're going to use, and you can do this many different ways. So we've done the random integer was our first example. The second one was the table. And then this is going to be using the hat method. So we're using 18 equally sized slips of paper. Remember that. Labeled 12 of them M to represent math majors and 6 of them S to represent stats. Shuffle the papers well and divide them into 2 piles of 9. Record whether or not one of the teams is made entirely up of math majors. Okay, so after we've shuffled them up, put them in our hat, pull out 9, put them down, take a look at the other pile, see if one of the two piles were completely made up of math majors. So here's an example of one trial. So we had all 18 pieces of paper, and here's one team. So Team A only had 8 math majors. Team B had 4 math majors. Okay, so this was one pile of 9. This was your second pile of 9. Okay, so in this trial, neither team was made up of entirely math majors. So in 29 additional trials, there was only one trial where an entire team was made up of math majors. So that's actually not that. So what does that mean? So how can we interpret this result? So only one trial in 30 resulted in a team with all math majors. So the probability of getting an entire team of math majors is only 0.033 or 3.3%. Because getting a team of all math majors is very unlikely to happen by chance alone, we do have convincing evidence that the names were not shuffled very well. So take a look at your answer. If it's a high probability, then they probably were shuffled well, and it was likely that one team could have ended up all math majors. But since it's not a very high probability that one team's going to be all math majors, we can probably say that he didn't mix the hat up very well, or she. So is it possible that the names weren't adequately mixed in the hat, or could this have happened by chance alone? So in this case, for the conclusion, you wanted to conclude that you have convincing evidence and whether or not it happened by chance alone based on the question. So the question says, could this have happened by chance? So when it says, could this have happened by chance, you want to find that probability and then make the decision, okay, was that a high probability or a low probability? Just make sure when you're writing your conclusion that you state you have evidence that proves the claim. You are never going to have proof for anything. Okay, we have no proof whether or not they mixed the hat up well. Okay, it's just evidence saying, hey, well, that's a pretty low probability, so I sort of think you didn't really mix the hat up as well as you should have. Okay, so in this section, what did we learn to do? Okay, we understood the probability as a long-run relative frequency, and we used our simulation in order to model chance behavior.